Let's continue onwards in chapter 14, and we're going to focus right now on Coulomb's law. Coulomb's law is a force law, so it's sometimes called the Coulomb force, and it's going to describe the interaction, the force between two charged objects. So consider these two positive charges. I'm going to call them Q1 and Q2, and they're going to be separated by a distance r. Now, we know from the discussion we had before that Q1 is going to be repelled by Q2. So this is the force on 1 by 2. And Q2 is going to be repelled by Q1. As to why they're Q's, don't ask. Now, if we want to be very particular, and we were very careful with our measurements, we would notice that these forces act along the line connecting the two charges. So they get repelled directly away from each other. There's no curving, no nothing. Now, knowing this, we might ask how strong is the interaction between these two charges? By that we mean, what is the magnitude of the force acting on Q1 and acting on Q2 because of this interaction? Interaction is just kind of another way of talking about force. This is going to be our last example, I guess, really, of a force acting at a distance. Gravity was our first one. Electric force, the Coulomb force, will be our second. So, based on the stuff that we had, the kind of observations we had, we noticed two sorts of things. We noticed if we had more charge, we had more force. So we saw this on our list of observations last time. You know, more rubbing led to a stronger interaction. We said that was more charge being deposited then. Also, if the charges are closer, we had more force. Now, if it were, a long time ago, you could conduct a whole bunch of experiments, discover the law would be named after you, but Coulomb did them. You can check your book for kind of the experimental results, and this is the form of the law that he got. That the force of Q1 on Q2, remarkably looks very similar to the force of Q2 on Q1, but for a change in direction because Newton's third law. Anyway, is going to be this. It's K Q1 Q2 over R squared. So let's run through this thing very quickly. What is Q? So Q is the electric charge. Be careful, electric, not electron. So this Q is just like the mass of an object. An object has a mass. An object has an electric charge. We're going to call Q. It's measured in coulombs. So the unit is coulombs. It's represented with a capital C. What is K? Sure, everyone is so happy to have another K. This K, it's lowercase. It is a proportionality constant, which means it's just there to get the units right. So it depends on what units you use. In SI units, where we're measuring forces in meters, forces in newtons, distances in meters, charges in coulombs, K is 9 times 10 to the 9th newtons meter squared per coulomb squared. That feels like a lot to remember, but if we come back to this equation, if K is in newtons times meter squared divided by coulomb squared, well, Q1 is in coulombs, Q2 is in coulombs, R squared is in meters squared, so we see this is just trying to get us to newtons, which is what we expect the force should be measured in. All right, so let's say we have two charges that are near each other, like so. Q1 with a charge of 4 times 10 to the negative 3 coulombs, or 4 millicoulombs, and Q2 with a charge of negative 4 times 10 to the negative 3 coulombs, or negative 4 millicoulombs. We're going to need to get very comfortable with scientific notation here because charges are generally going to be very small. It is uncommon to see a charge of a coulomb just sitting on something. More commonly, we're going to see charges of nanocoulombs even. We're going to come to that later. So, let's take a look. We got this equation again. F equals K Q1 Q2 over R squared. We notice it's the magnitude of the charges because the strength of the charge just cares about how much charge there is. If it's attractive or repulsive depends on the signs of it. If they're the same sign, the same thing, we have a repulsive force. If they're opposite, we have an attractive force. We've already kind of ironed that out. This is just then talking about really the magnitude of this force, which we write normally just as an F. Without a vector symbol, but regardless. So let's do this. We got to be very careful. So 9 times 10 to the 9th. Q1 is 4 times 10 to the negative 3. Q2, the magnitude or absolute value of Q2 is also 4 times 10 to the negative 3. I'm dividing by 1 squared, which is just going to be 1, so that's not too bad. So if we look at this, when we're doing scientific notation, we're going to group up all the coefficients, so 9 times 4 times 4. And we're going to group up all the powers of 10. 10 to the 9th times 10 to the negative 3 times 10 to the negative 3. This whole thing, oh, why are lines so hard, is divided by 1. So really, yeah, just that. Now, we're going to go and do this. 9 times 4 times 4. If you're really good at mental math, you would know it's 144. Or if you just typed it into a calculator right next to you, you would also know that. And then we need to go and look over at this. You can also know that it's 16 times 10 minus 16. Just saying. Anyway, when I'm multiplying powers of 10 like this, when they have like bases, any exponent has like bases, I'm going to add the coefficients. So it's 9 minus 3 minus 3. That is just 10 to the third. This is in newtons. That is a honkin' big force. And that's with just, millicoulombs of charge. So that gives you an idea of how small charges are. If we had millicoulombs of charge sitting on any regular charged object, it'd be enough to fling us around the room pretty fiercely. So that's not what happens. All right. So that's how to use that. Now, some things that we may need to know here. Some useful information. We need some new prefixes. First, micro. So micro something. Not micro machines, but something like a micrometer. Or micrometer sometimes, but anyway. Micro, which is going to be abbreviated by the Greek character mu. It's like a backwards U with a long tail. Is 1/1,000,000th of something, or 10 to the negative 6. So a micrometer, or a micron, 1 mu m is equal to 1 times 10 to the negative 6 meters, or 1/1,000,000th of a meter. And then nano, abbreviated with a small lowercase n, 1/1000,000th of something, 10 to the negative 9. A nanosecond then is 1/1000,000th of a second, 10 to the negative 9 seconds. And lastly, the electron charge, not the electric charge. So this is an interesting thing. It turns out every charge is built up of integer multiples of the electron charge. We call this the quantum of charge. Quantum is a word meaning kind of the smallest chunk of. So we can think sort of US currency, at least of physical currency. The penny is the quantum of US currency. Every amount of money you have can be built up from pennies. So in the same sense, the electron charge, not the electric charge, the electron charge, the charge of an electron, is this 1.6 times 10 to the negative 19th coulombs. It is tiny, right? It is less than a billionth of a coulomb. 1/10 of that, basically. But oftentimes we want to talk about charges in the context of how many electrons there are. So this value is very important. I can take any charge Q and represent it as some number of electrons times E. So this is any old charge. This is the number of electrons. And this is the charge per electron, right? Basically saying if I have, 10,000 pennies and each penny is worth this much, this is how much currency I have. If I have 10 million electrons and each electron is worth this much, this is how much charge I have. It's not a terribly complicated concept. The fact that we write an equation for it is a little overkill. It's basically just saying if each electron is worth this much and you have this many electrons, how much charge do you have? It's a counting problem. But there's one more thing in this chapter. And we had kind of an interesting combination of ideas is to share charge between conducting spheres. So let's say I have 3 identical conducting spheres resting on insulating stands. Insulating stands so that the charge that's on them stays on them, and so I can move them around and stuff without charge leading off. So let's say these spheres, I have A, B, and C. A is starting with a charge Q, B starting with nothing, C starting with nothing. Now, I'm going to take B and bring it into contact with A. So if I do that, here's A right next to B. What do you think is going to happen? I have this charge, this positive Q on A, and now B is right there next to it. This charge is swirling around on A, trying to get out, and this identical sphere comes up, touches right next to it. So what's going to happen? Well, I'm going to wind up with that charge splitting. So I'm going to wind up with half of it staying on A, and half of it going to B. So when I separate them, come on. Just sitting here poking my screen ineffectively. When I separate them again, now A has lost half of its charge. So it's gone over to B. I could do the same thing. Still got C hanging out over here, wanting to get on the action. Let's say C comes over to B. Well, so now the same kind of thing happens, right? I have this total charge of Q over 2, and it's going to split between the two of them. So half of that is Q over 4. And it's just kind of an interesting consequence of, thinking about quantifying charge, how much charge you have, and kind of these rules that we have for conductors. You could then ask, what is the force between these two? What is the force between these two? You could do all sorts of fun stuff. And maybe we will. But for now, this is a good starter talking about, the big idea, Coulomb's law. This Coulomb force between charged particles depends on their charge and their separation. And it's just this one equation that we're really trying to play with here. Okay, have fun.